let us do one thing. We need to also have completeness in terms of the kind of series elements, series pass elements that we are going to introduce, right. So we said that there is a possibility to use NMOS as a series pass element because it has a lot of attractions. For example, the RDS of NMOS at MOSFET transistor, NMOS is low as compared to PMOS, but it is also always a good idea. So this is what we said, it is always a good idea to actually sketch the circuit diagram of a PMOS series pass element as well. So let us do that, let us put that thing so that we understand exactly how both the circuits really work, because in the case of in the NMOS case you needed a charge pump, right, to ensure that the gate control is there, because the gate voltage has to be higher than the output voltage. So and that is the only way you can do that is to introduce a charge pump. Charge pump circuit, how it functions, we will worry about that separately, but that is what will be required in the NMOS case. But in the PMOS case you do not have to worry about it, because simply getting down the gate voltage or increasing the gate voltage will ensure that conductance of the series pass element is taken care. So let us quickly put down that circuit and then quickly explain a few things so that that part of the study on LDO is also completed. So let us start with that. So let me take a fresh page and put back our famous circuit where we talk about the PMOS element. So PMOSFET, P channel MOSFET. So now drain is the output, source is the input and gate is the control point, and as usual feedback comes from the center point. You have R1, you have R2, and you know this thing now very well, this is Vref, right, and this is incomplete if you did not have an output capacitor. This is also incomplete if you did not have an input capacitor, right. C out, C in, they are all very important in a MOSFET, because in a LDO, because these are the components that actually give you stability, right. These are the ones that give you the stability of the controller. Now it is quite simple, right. So if I load, now if I load, so let us say the output drops. So the output drops for some reason. So so the reason why V out might actually drop could be because of two possibilities, right, from a broad perspective. One is increase in load current, increase in, so V out falls, I will say. Why does V out fall? It can be because increase in load current, which is nothing but I load has gone up, has increased load current I load, or it could also be because the input voltage has dropped. These are the two possibilities, right. Now the way that you essentially take care is you bring down or increase the gate voltage. This is the gate, right, essentially that is what you will have to do. Now if V out drops, Vg, this is gate voltage is brought down, right, is lowered with respect to V in. Okay. Nothing but the source point. So, you can see that this is what ultimately a PMOS series pass element control is all about. You would have had a charge pump here or a V bias which is fed from an outside. Recall you had a point here which essentially was connected. I will just draw it in dotted line so that you do not get confused. This was either a charge pump slash V bias which was connected to, if it is in the case of N channel MOSFET, but in P channel you do not have to worry about that. Directly if you lower or increase the gate voltage with respect to V in, you have a good control. So, this is a nice thing which in the case of PMOS circuit you could essentially build a simple system. Now, one important thing that you will come across every time the when you select an LDO. So, here is every time we have this problem of selecting, right. So, let me take a new sheet, I will remove this and I will go here. You want to select. So, selection is our problem, selection of an LDO. Not only selection, you may have to look at the data sheet. Slowly we have to discover the data sheet, only then you actually know how to choose one. I will draw a very simple intuitive result, okay, and let us see how to build the story from here. Typically this is the I load, okay, this is the I load. Let us say for some reason you have chosen I load as 8.8 amps, which is here, right. This is what I am saying, this I load, this is chosen as 0.8, sorry, where is the point here? Yes, this is the point. For some reason you have chosen 0.8 amps, right. So, let me connect back. So, this is your I load which is 0.8 amps. You have to look at the data sheet and always discover for this load current what is the dropout voltage. This is, so this axis is dropout voltage and this axis is the load current. So, you can put here 0.2, 0.4, 0.6 and 0.8, it is not uniform. So, let me move it a little bit so that we show 0.8, this is 0.4, this is 0.2, this must be 0.6, right. This is 150 millivolt, please note this must be half of that 75 millivolt and this is 0, right. So, look out for data sheets which essentially give you this kind of graphs, view graphs. I have not completed the story here for you. What you should also look at is what is your V out. This is at what V out? Let us say your V out is set to 2.5 volts, again insufficient spec. This is specified at what junction temperature, okay. So, you cannot escape looking up these additional parameters as well. This of course you have to look up because you would have designed your LDO for a given output voltage, but you must look out for this important parameter as well. And why is this important? This is important because of this result. Let me again redraw and show you. Let us put amps, in other words let me put I load I will just redraw I load, which is, please note, this is what I mean, this is that I load, and let me draw the dropout voltage, right. It turns out that it will be something like this. In fact, I should make it a little being a bit unfair. So, let me make it a little more uniform. Okay. Let us say that this region is the 0.8 amps. Now, this is minus 40 degrees, this is plus 25 and this is plus 125. So, now you see, put back the numbers you know very well, this is 150 millivolt from the previous this result. You can see now this has gone up, which means there is going to be more power dissipation, across the LDO. Why? Because the dropout voltage has increased, right. It has to maintain a higher voltage differential and has to drop sufficiently high voltage, so that you can continue to draw this load current of whatever we specified. This is clearly an important parameter which you must consider moving forward on design on the choice of the LDO. Now, there is one parameter which will keep sort of coming back to you each time on the LDO, and that is with respect to the loop gain. Okay. So, why is this important? So, let us put back a very simple diagram here, but this time we will abstract it so that we do not get, we do not mention too many things on this particular thing. So, let us just put down a very simple diagram to intuitively explain again this thing of loop gain. Remember your error amplifier, this is the LDO has an error amplifier, right, and the error amplifier is essentially will have a gain, right, it will have a gain. So, that is V in, this is the feedback, and you know what this is, Vref. Please recall the V out formula, right. Let us see if we actually put that down earlier, so that we actually know from whatever we wrote previously. So, let me pull that out and see if we I do remember having written that down. So, okay, the V out. So, I think we should take this will be helpful. V out, go back to the operational amplifier basics, you will find is nothing but Vref times, oh maybe R1 by R2. Right. This clearly indicates that the error amplifier is always trying to match the output, always looking up, monitoring the V out and trying to match to ensure that the difference between Vref and V out is always very very small, right. This is a simple expression for actual output voltage, which is, this is nothing but the gain term which is coming from these two resistors. Okay. So, coming back, this is the feedback, you know the V out here, this is nothing but Vref times 1 plus R1 by R2. Okay. And this obviously is the gain feedback, this has a gain and this is the gain parameter of interest. So, question is this, why are we discussing amplifier gain and all that? Basically if V out is being tracked closely, right, this is possible only because of the high gain, right. So, sensitive, because of the high gain it is able to sense the track the V out very very accurately. So, moment the ability of the LDO the LDO loses its ability or has loss in high gain, you are in, the LDO is not anymore going to function like a regulator. Okay. So, the gain of the LDO is so critical, right. Now, the gain of the LDO also has to do with its ability to reject ripple, okay. And there is a term which again data sheets will look at, and which essentially leads us to a very important data sheet parameter, which is called power supply rejection ratio, okay, PSRR as it is called. So, PSRR also is nothing but the PSRR is simply nothing but as 20 log of V out by V in. We will discuss PSRR in detail later, okay, later, but I have to connect this PSRR, I have to introduce this term because it is related to the gain of this error amplifier, the gain that is provided by the error amplifier. What am I trying to say? In summary is the high loop gain gives you the required regulation, okay. High loop gain because of its high sensitivity is able to do the regulation, and so much so you may also have to look at situations where this loop gain lowers. What are the situations under which loop gain lowers? For that you must look at the ability of the op amp the LDO, the ability of the LDO to reject ripple, okay. So, let us connect that together. I will draw another picture here and everything will sort of get summarized. It turns out the ability of the error amplifier, the LDO, so this is essentially the PSRR expressed in dB, okay. This is minus 70, this is minus 60, minus 50, minus 40 and so on. The deeper the better, right. So you can say an LDO which has minus 70 PSRR is much superior compared to something which you get an LDO which has a PSRR of minus 50. Clearly it is a much, the minus 70 the LDO is a superior one, that is one part. But all of that, how well does it get supported in terms of its response becomes critical. I will put one nice picture here, I will just continue this story here. This is frequency, okay, and this is PSRR. It turns out the same LDO, okay, behaves something like this. Please note that this is a log picture, you have to, because I mentioned it in dB, this is all, this is a log, right, but just for some simplicity and quick understanding let me put it this way. This is lower frequency and this is higher frequency, sorry, this is higher also lower frequency, but these two pictures are different. This is at low load and this is at typically at higher load, okay. Then you can draw something like this and then you can draw something like this. So please note this is a log, I did not elaborate, but I want to bring out a very important point here. The point is the loop gain plays a critical role. Under low load, what do you mean low load? What we mean by low load is just this, that the I load here, we are referring to the I load. I load, if I load is only 10 milliamperes, you get better loop gain, higher loop gain as compared to I load at 100 milliamperes, okay, this is greater. Also you have to bring in the other point that the x axis is frequency at low frequencies, at lower frequencies. Now you can see this is the ability of the LDO to reject ripple, okay, its ability to reject ripple, and its ability to reject ripple is much superior at lower frequencies and at low loads. But if the load current increases, then you have the problem that LDO's loop gain actually gets lower, and as a result its ability to filter the ripple, input ripple is also poor, and the cause for all this is indeed, as I said, the fact that the loop gain takes a beating, particularly as you move higher in frequencies and higher in loads, higher in I load. When the I load increases, I load current, I load when I say I mean current, output current increases. So all this clearly shows that LDOs have finite bandwidth. In fact this is a clear indicator, right, this picture itself tells you, you can see that PSRR is reducing because you are going closer to 0, this is minus 30, minus 20 and so on, is reducing its performance, its ability to filter out ripple, its ability to filter out noise is also reducing as the frequency increases and as the also with respect to the increase in load current, okay. All of this means there is a problem that the loop gain is not, you can't maintain a high loop gain because you do not have an infinite, you do not have an infinite bandwidth. The bandwidth of the LDO is finite. So, bandwidth of LDO is finite. Look out for this important parameter, because it is linked to the power supply rejection ratio or ripple rejection ratio as well. So, in summary, the whole system, if you look at the LDO, the performance metrics, if you start putting down performance metrics for an LDO, again I am driving you in the direction of the data sheet, please note. Okay. One important parameter that will come to you will have to see is with respect to accuracy. Okay. Now, why is this important? Why is this accuracy so important? Because it comes from LDO to LDO, the fabrication process is a variable. Okay. You can't, as much as you are able to control it, it can have certain variability. So, it can come from fabrication process, and it can also come from the ability it can come because of temperature. Temperature is another important parameter, and therefore, you basically it is all about the ability of the circuit to respond to basically the ability of the circuit, right, basically the ability of the circuit to respond given the change in temperature. This is another these are the two important parameters which basically you have to keep in mind. So, you will have to look out for a parameter which will highlight the accuracy of the LDO. Another important so this is one thing. Second thing is, you may also want to look at tolerance. Okay. Again, this largely comes from fluctuations in fabrication. Okay. Fluctuations in fabrication. See, it brings down to a very important point, that you go back to this basic expression, right. If you go to this basic expression, you clearly see this plays the most vital role. What is this? We did talk about it. Vref is the band gap reference, REFERENCE, band gap reference voltage. If this fluctuates, then V out will also fluctuate. I hope you will agree, because we have been discussing LDOs so much that V out depends on this Vref, right, and if this fluctuates, this V out will take a beating as well. So, all the control loops, all of it means that you must look at tolerance of the LDO, which you may want to the data sheet parameter should tell you something about the tolerance of the LDO as well. So, other thing which perhaps we will have to worry about is there are other parameters as well. For example, there is something called gain error for an LDO. Okay. What this simply means is the sensitivity of the system to fluctuations, sensitivity of the system to fluctuations ultimately rests on the gain, right, gain across the loop. Okay, very very important. Infinite loop, infinite gain LDO does not exist. Does not exist at all. You can't be talking about that, right. So the basic thing about the fact is that unless sorry I think yeah, unless, so what is the gain trying to do? The gain is trying to follow, you are adjusting the gain so that Vref is always equal to Vf, so Vfb, that is the feedback that you get, you are always trying to adjust that. Any error that you are not able to, if it becomes an approximation, so I think it is good to put it the other way, the V feedback ideally should be equal to trying to match Vref, this is ideal, but in reality it is close. Now this means this is the error in gain, right, that indeed is the gain error for an LDO. So let us now in the next, when we start further, what we should do is summarize all this and take a data sheet, open a data sheet and look up some parameters, and see if we can explain other things as well, things like line regulation, ability for the LDO towards line regulation, load regulation, okay, and then see also try and see power supply rejection, ripple rejection, this one, and look at the response and then look at some practical circuits, how people have used LDO. All of this will perhaps allow us to choose this very important system component. So now let us see the working of a buck converter. Essentially you can see that we have a series pass transistor and the other transistor, every time the series pass transistor switches off, the other transistor switches on, and then you have the current circulating through the load from the inductor to the load and back. What you have here is the usual setup, you have a current electronic load which is placed on top of the power supply. Left side is the input voltage and input current that you see on the left side of the power supply. The right side is the output voltage and the output current that you see. You can see that this experiment is is basically what we are performing is to understand the power loss. Okay, essentially what is the power that is being delivered at the input and what is the power that is delivered at the output. You just want to find out the difference between the two, and this, in fact, if you do this experiment you understand many related things with respect to efficiency and so on. So now you can see that input is here set at 6 volts and the current here is so let us go from the output side. I need to buck whatever is the input to an output of 3.3, and I need a current of 100 milliampere. In order to do that, the input which I have said, in order to get to this I am trying to buck an input voltage of 6 volts. Now for when I apply 6 volts at the input, the current consumed is 125 milliamperes in order to deliver 3.3 volts bucked output and a 200 milliampere current. As you can see that there is a very small difference that you see at the you see at the output. This electronic load is right now connected to the output of the buck converter. So this experiment was conducted over range of load currents starting from 50 milliampere to 200. What you see right now on your screen is the fact that the load current is at 500 milliamperes. In fact this experiment is conducted up to 1500 milliamperes, and we will take you directly there. Okay, so this is a snapshot of 3.3 volts and the output load current which has been set to 1.5 amperes. Now what you do, you have a set of readings, right, because you have done a sweep of different for against different load currents. Now what you do, you go and change the input voltage from 6 to 12 and repeat the whole experiment. Then what you do, you change the input voltage again to 18 volts and do the whole experiment. Then you again set it to 24 volts and do the whole range of experiments, and also you do the whole range of experiments for 30 volts. In other words, for different input voltages you conduct the experiment by varying the load currents. Now what is very important in this stage, at this stage, is what is the switching frequency. The switching frequency under which this experiment is done is for 250 kilohertz. What you can also do is repeat the whole set again for 500 kilohertz switching frequency, right. At the end you will end up with a nice set of nice table, and from there you can actually make out what is actually happening. So now you can see that we are showing you for an input of 10 volts, and yeah, so no, actually it should be step 2 should be 12 volts. 12 volts, yes, the input is set at 12 volts, and as you can, as I was mentioning, 18, 24, 30 for 250 kilohertz, and then again 6, 12, 18, 24, 30 for 500 kilohertz. As you can see, input was set to 50 milliampere and then we did a sweep, and so all these are all essentially all the tables. Switching frequency there was 250, this is 500 kilohertz, and then we generated all these tables, right, whole range of measurements, and then this is the power loss. As you can see, this is for 250 kilohertz, and you will see that V in 6 to 30 volts, the power loss for small currents you have 24 milliwatts, and it goes up to about 47 milliwatts for 50 milliamperes. And you can actually go directly and also look at what actually happens as the higher currents increases. You have 977 milliwatts of power loss and 1481 milliwatts for 30 volts. Change the switching frequency to 500 kilohertz, you get a set of range of values 25 milliwatts to 46, comparable to that of the other one and quite comparable to also the higher thing, higher currents. But I want to draw your attention to this particular table which is for 500 milliamperes. You can see 200 is more than 3 times 623, and here it is 196 and it is 2.5 times, something roughly 2.5 times. Keep this in mind, this should somehow show up as efficiency numbers, right. Again you concentrate here, you will see 89, 72 for 250 kilohertz, this is the efficiency, and for this current, and of course efficiency is fantastic, perhaps quite very good also for the same current at 89% when the input voltage is 6 volts. So it is quite a high number. Essentially what we are saying is that this table should be used, should be prepared, and find out in this matrix where do you get the maximum efficiency and whether it matches the required load currents, load output power the load power that is required, whether it will allow you to get into an efficient the buck converter gives you the best efficiency. Why is that important? Because energy harvesting is an input to all these systems, and therefore unless you have high efficient systems, these systems may not give you good battery life. Thank you.